Hi everyone, I am Daehyun Kim, and I'll be sharing what I have been working on with Enamul Hoque, Juho Kim, and Maneesh Agrawala. We're all familiar with PDF viewers. This is Adobe Acrobat Reader showing a Pew Research report. And as you can see here, it contains many pages. Like many documents, this one has tables and text that refers to the tables. For example, this sentence, equal numbers of men and women said they like time, refers to this table below. Looking at this more closely, the sentence refers to this set of cells, the percentages of men and women who don't have time to use the internet. We've built an interactive PDF viewer that looks like a normal PDF viewer. It connects text with the corresponding tables. So when I click on the sentence in the text, the corresponding cell is highlighted in the table. The goal of our work is to automatically extract references between sentences and tables to improve reading experience. Before I tell you how our system works, I need to talk about some of the related works. Kong extract references between text and visualizations using a cross-sourcing pipeline, which makes it hard to scale. In contrast, our work is automatic. Govindaraju et al. Joined the data in a table with information in the surrounding text. We focus on a different problem, extracting references between text and tables to improve the reading experience. Finally, Pasupan and Liang have developed a natural language question answering system for tables that assumes questions of a specific form. We also use natural language techniques, but do not rely on the same assumptions in extracting the references. Here's the table and the sentence that we've been looking at. And remember that the correct reference contains all of these cells. But a simple text matching approach only finds these header cells. And it misses all of the cells because there is no direct text match. Here's our approach. The input to our pipeline is a table and any sentence in the document. First, our system extracts the structure of the table. Then our system performs a preliminary matching between phrases in the sentence and cells in the table. Finally, our system amends the reference from the previous stage using this table structure. As a result, we obtain the references between the sentence and the table. In stage 1, our system extracts the table structure using a simple row-based approach. First, the table may contain a title cell that describes its overall contents. A column header describes contents below it, and a row header describes contents to its right. For example, percent of online men in the second column describes the numbers underneath. Finally, the data cells hold the specific data values reported in the table. As a first step of cell classification, our system finds the largest contiguous rectangular region, including the lower right corner of the table, with no merged cells. We call this the maximal regular grid. Our system looks at the cells in the leftmost column of this maximal regular grid, and if the data type of these cells are different from the cells to their right, we classify them as row headers. Same goes for the topmost row. And our system classifies the rest of the cells as data cells. Cells outside the maximal regular grid are headers, potentially except for the top row. If it contains a single cell, we consider it the title row. During this stage, our system also propagates information in the header cells to the data cells. Here, the system detects the percent sign in the column headers and propagates this information to the data cells. In the second stage, our system matches cells in the table with phrases that explicitly describe them. In our current example, directly matching words between the text and the table can find the correct matches for men and women. But matching the phrase lack time with don't have time requires looking at the semantic similarity of the phrases. In order to do this, we first take the sentence and build its phrase tree using the Stanford Core NLP toolkit. The words lack and time together form a verb phrase. This phrase along with the word they form a subordinate clause. And this together with the word said forms a verb phrase. Continuing this process gives us the phrase tree for the entire sentence. From this tree, we want to find the largest phrase that matches with the table cell. So we begin with the root node and check if the phrase and the table cell are semantically similar. As a measure of semantic similarity, we vectorize the two phrases using word2vec and use the cosine similarity of the two vectors. The two are not similar, so we continue down the tree, checking if the word2vec vectors are similar between phrases at each node and the cell. For simplicity, we will skip the left subtree and continue to the right subtree. Said they lack time is not similar to the cell. Said is also not similar to the cell. Continuing down, they lack time is not similar to the cell, and they is not similar to the cell. Now, lack time is semantically similar to the cell, so we match them. At this point, we have all of the headers matched. We will match the data in stage 3. But before we go to stage 3, let me show you another example in stage 2. Here, the sentence says decreased 1%, but it doesn't directly match any of the table cells. There is, however, a minus 1% in the table. Our system starts by detecting the 1% in the sentence using the Core NLP entity recognizer. It then detects modifiers for numbers and uses them to update the detected number. Here, it interprets decreased 1% as minus 1%. Similarly, 1.6 billion doesn't match directly with any cell in the table. But there is a 1.63 billion in the table. Again, we start by using Core NLP entity recognizer to detect 1.6 billion in the sentence. Then if the number in the table rounds to the number in the text, or vice versa, our system matches them. Here, 1.63 billion rounds to 1.6 billion, so our system finds a match. Finally, in the last stage, we fine-tune the matches found in stage 2 using the structure of the table with a rule-based approach. In stage 2, we detected explicit references, but not implicit references. In our example, we didn't include the 229s, the values being compared in the sentence. To handle this, we include cells in the intersection of matched headers. As a result of this rule, we capture implicit references to data cells. The next rule handles ambiguities in matches found in stage 2. Performing stage 2 on the same table as before with the sentence 29% of men said they don't have time results in the phrase 29% matching with two cells in the table. To handle such ambiguities, we filter out matches that do not belong in this intersection of the matched headers. For more rules we use in our system, please refer to our paper. Let's first recap some of the matches our system successfully captured. For these two tables, we have seen how our rule-based approach generates these correct results. But it can also generate errors. For example, it can generate false negatives where it misses cells. In this example, the correct reference includes the column headers % of men and % of women, and the row for don't need it. This is what our system generates. It is unable to understand that the word they refers to women in a previous sentence and misses information in the reference, resulting in a false negative error. Our system may also generate false positives, where it contains extra cells. Here, there is no reference between the sentence and the table. This is what our system generates. All of these are wrong because the sentence is not relevant to the table and ends up including wrong information in the reference, resulting in a false positive error. We quantify the performance of our system by comparing the resulting references with gold references. Specifically, we extracted tables and sentences from a corpus of Pew Research reports and academic papers. To create a gold set of references, we manually and independently generated references between the sentences and the tables and collaboratively resolved conflicts and reached consensus on the references. We also use Kong et al.'s references between text and charts dataset to confirm that the method generalizes to data extracted from charts. Over all of the three datasets, the system generated correct references in almost half of the sentence table pairs. The system missed information and generated false negative errors in 30.5% and included wrong information and generated false positive errors in 11.2% of the sentence table pairs. Another 9.5% included both types of errors. We also found that the performance of the system was somewhat consistent across all of the datasets, meaning that our pipeline generalizes across the collected datasets. The error rates may seem high, but this problem is hard, and we see our work as a first baseline for reference extraction. Moreover, we will show in our user study that even with these errors, people are better off with our tool. Using these references, we built the interactive document reader that we have briefly looked at. In addition to what we have previously seen, there is a side panel. The side panel shows the table relevant to the text at the center of the screen so that the users can see both the table and the sentence in one view. As we have seen before, clicking on an underlined sentence highlights the relevant cells in the table so that the user can easily locate them. Also, clicking on a cell in the table highlights and scrolls to the text that is relevant to the cell so that the user can easily navigate to the relevant text. We ran a user study to quantify the usefulness of our system. The hypothesis that we wanted to confirm through the user study is that our interface facilitates reading documents with tables despite the errors included in the generated references. We ran a within-subject study with 14 participants. The task that the participants were given is to annotate references of a given sentence in a table with or without our interface. The highlighting interface showed the references generated by our system. The findings of the user study indeed supported our hypothesis. There is a 26% difference in accuracy between when the participant used our interface and when they did not. And this is significant. So this already suggests that we can accept the hypothesis. Moreover, the 47% accuracy without our interface indicates that this is a relatively difficult task. Also, the participants spent 11 less seconds with our interface than without. The difference is again significant, and thus further supports our hypothesis. When asked to report the usefulness of the UI, with 5 being very helpful, the participants in general reported that the interface was useful with a mean score of 4.1. While we believe that this is a step towards improved document reading experience, there are multiple possible directions, but here's one of them. In this work, we have confirmed that our pipeline generalizes to data extracted from visualizations. But there's more work required to correctly handle visualizations, such as recognizing visual attributes. For example, here, we have to understand that the dark blue refers to rain. So that sums up my talk, and you can find out more about our work at the project website available at this link. And I would like to thank all of those who have made this work possible. I am happy to take any questions.
So we have time for question or two. Question coming? I don't know. I have one quick question. Since, of course, there are, as you pointed out, false positives, false negatives, could you have a system where the users can fix those errors and annotate themselves the PDF for future readers?
So I think that is definitely an interesting direction. So we can have a system where the readers, as they read the document, they fix whatever see that's wrong, and maybe the system smartly learns what's fixed, and maybe that helps to perhaps machine learning approaches that will result in better results in the future. Another approach that some people have brought up is that we can use this for authoring tools, where authors can actually embed the references in the document they generate. So in that case, as we have seen, even with the 50% errors, it is able to help the users. If the authors are able to include the correct references, I think that it will be able to help the users even more than currently.
Okay. Well, we don't seem to have other questions. Takeo?
Yeah. I'm just curious. Is there any technology or paper that automatically generates natural language explanation for a given graph or chart, table?
That's the other way around. So you generate the sentences from the table.
Maybe this is useful for blind people.
I am not really sure.
Yeah, just a question. Yeah.
Okay, thank you.
Okay, well, thanks again. And let's thank all the speakers in the session.